Good morning, students. Today we will start chapter 13, probability. This is a topic which we are studying from class 9th. In 9th class, we have just get an idea of the definition of probability. And in class 10th, more than that. And in class 11th, we used algebra of sets in the probability. Now in class 12th, we will start this probability chapter with the topic conditional probability. Now, what is the conditional probability? Let's start to read that concept. Conditional probability, this 13.2 point. We have discussed the methods of finding the probability of events. If we have two events from the same sample space, does the information about the occurrence of one of the events affect the probability of the other event? Hit the question mark, which we have to check. Let us try to answer this question by taking up a random experiment in which the outcomes are equally likely to occur. As you know, what is the meaning of equally likely? Each and every result has its its probability same. If a number of outcomes are 10, then each and every element which is the result having the probability same. Or you can say, if there is a sample space having elements 8, HHH, HHT, HTH, THH, like this, all these, it means probability of each outcome is same. Each outcome is this. I am just circling it. All these 8 outcomes have same probability. It means that the event is equally likely. Okay. Now here is the question. What is the conditional probability? What we have to do for the concept conditional probability? Let's take two events, E and F. Let's take, yes, E and F, two events we are taking. E is the event, at least 2 heads appear. And F be the event, 1 coin shows tail. At least 2 head means 2 head and more than 2 heads we have to taken from the sample space. Number of outcomes are 4, 3 heads, and these are the 2 heads, 2 and 3, both cases. 4 outcomes are there. For F, first coin shows tail. These 4 outcomes are there in the event F. Now probability of event E. First HHH. 1 is a favorable case and total sample space elements are 8. So 1 upon 8, 1 upon 8, 1 upon 8, 1 upon 8. All are having the same probability. It means all are equally likely, and total probability is 1 by 2 for event E. Same as for F, the probability is 1 by 2, and common part of these two elements is the outcome, that is HTTHH. The common is H, so THH. So only one element which is common. So probability is what? 1 is a favorable case and total elements are 8. So 1 upon 8. Here we have done probability of E, probability of F, and probability of common part, that is E intersection F. Now suppose one condition is given to you. Condition is, just read the condition. Suppose we are given that the first coin shows tail. It is given that first coin shows tail. It means we are talking about the occurrence of event F. Then what is the probability of F? It means what is the probability of E if F already happened? We'll write like this. We want the probability of E and slash sign and F. If F is already happened, it means probability of E you want to calculate if F is already happened. Now, it means what? What's the meaning of this now? With the information of occurrence of F, we are sure that the cases in which first coin does not result into a tail should not be considered while finding the probability of E. It means for E, you have to take the sample space F instead of S. This information reduces our sample space from the set S to its subset F for the event E. For the event E, you have to take the sample space as F event. In other words, the additional information really amounts to telling us that the situation may be considered as being that a new random experiment for which the sample space consists of all those outcomes only which are favorable to the occurrence of the F. Now it means if you are taking F as a sample space and you want to calculate the occurrence of E, only one element is there which can be considered, that is the common part which we have, that is THH. Now probability, this is a favorable case 1, but sample space here F having elements 4. So probability of E if F is already happened is the 1 upon 4. This is the important part. What is a given? F is already happened. Now we can write, as I told you, probability of E if F is already happened is 1 upon 4. Now how to calculate this? By using the formula. What is the formula? Now here is the formula. You have to learn that formula. Yes, probability of E if F is already happened, this. Probability of E if F is already happened is probability of number of elements in E intersection F upon number of elements in F. This will give you probability of E if F already happened. Suppose you want probability of F. E already happened. What is the change in the formula? It means you have to take intersection of both E and F and number of elements in now in E, not in F. When F is already happened, divided by the number of elements in F. If already happened event is E, then number of elements E is there in the denominator. So this is a formula. This is the first formula. You have to learn these. Now here are a few properties which you have to learn. Let's see those properties also. Where you must know denominator should not be equal to 0. This is the condition. You must remember it. Now this formula we have discussed. Now properties of conditional probability. Now suppose probability of sample space you want to calculate, and if F already happened, intersection of both divided by which is already happened event, that is F. It means probability of F. And intersection of F and S, that is equal to probability of F. S is a greater one, F is a smaller one. Intersection of greater and smaller is comes out smaller one. Probability of F upon probability of F, both are cancelled and it is equal to 1. Same for F, if probability of F, if F is already happened, then again it is 1. Now property number 2, if A and B are two events of a sample space S and F is an event of S such that probability of F is not equal to 0, then as we know the formula of probability of number of elements in A union B is equal to number of elements in A in plus number of elements in B minus number of elements in A intersection B. And we are applying the same property on the conditional probability concept. So probability of A union B if F is already happened. This is if already happened. So probability of A if F happened, B if F happened, and A intersection B if F happened. Now you have to put the values and you will get the value, concept, or you can get the answer. If you want probability of A union B and F is already happened, then you will do like this. Now if the A and B are disjoint, nothing is common is there, nothing is common there, then it means 0, A intersection B is 0. So third one part will be 0. So probability will be equal to probability of A union B will be equal to A if F happened, B if F happened. Intersection is 0, that's the third term is 0. Now probability of A union B, if F happened, can be written as like this. This is a proof. Now here intersection is 0. Now we have discussed it. Intersection part is 0, then third part, this one is 0. So only two terms are there. Now probability third one, probability of E not if F happened. Not occurrence of E if F is happened. Already happened, you can say. So what? 1 minus probability of E if F happened. Remember this property also. E naught, if you want to calculate, it means same as we have studied in the class 10th or 11th. Probability of E naught is 1 minus probability of E. So if you want probability of E naught if F happened, so it will be 1 minus probability of E if F already happened. Okay. Now here are examples. Let's discuss examples of exercise 13.1. Here's a probability of A is given, probability of B is given, intersection of A and B probability is given. You want probability of A if B happened. First of all, you must know how to write down the formula if it is given to you. It means intersection part is in the numerator and which is already happened probability which is in a denominator. Now put the values and you will get 4 upon 9. Now in example number 2. A family has 2 children. What is the probability that both the children are boys given that at least one of them is boy? Now first of all, you have to know the sample space. Both are girls. First is girl, second is boy, and first is boy, second is girl. Like this. Here is the sample space. Both BB, GB, BG, and GG. What is the meaning of B? B means boy, G for girl. This is a sample space. Now E is a event. Both children are boys. And F, at least one of the child is a boy. At least one is, it means greater than equal to 1. All values you have to take. So E having element only 1, both are boys. And in F, 1 and more than 1 boy means BB, GB, and BG. The intersection part is this one. Probability of E you want to calculate, it means both of the children are boys. Probability of E you want to calculate if F is already happened. It means formula is this one. Put the values 1 upon 4 upon 3 upon 4, that is 1 upon 3. Now this is the example number 2nd. Now example number 3rd. 2 cards numbered 1 to 10 are placed in a box, mixed with thoroughly, and then one card is drawn randomly. If it is known that the number on the drawn card is more than 3, what is the probability that it is a even number? Now what is a given one? It is known means what? If it is known that number on the drawn card is more than 3. This is the given part. Given. It means this is, suppose you want it is an even number, it is A. Number is A on the even card and B is already happened. This given is B. So you want to calculate probability of A if B already happened. Already happened means it is known to you or it is given that. Okay. That event is known as the already happened event. The A is number on the card drawn is even and B be the number on the card drawn is greater than 3. Now sample space having element 10 and A means even numbers 2, 4, 6, 8, 10. B means number greater than 3, 4 to 10. Now intersection part is this one. Probability of A, probability of B, probability of intersection. Now you want probability of A intersection A if B happened, probability of A intersection B divided by already happened event probability. Now you have to put the values 4 upon 10, 7 upon 10, it comes out 4 upon 7. Now example number 4. In a school there are 1000 students, out of which 430 are girls. Okay. It is known that out of 430, 10% of girls study in a class 12. Okay, 10% of the 430 means 43 girls are studying in a 12th class. What is the probability that a student chosen randomly studies in a class 12th given that part is student is a girl. Girl kitni hai? 430. It means how many are girls? It is given to you. It means this will go in a denominator. Probability of this will go in a denominator. Now intersection part you have to calculate. Let's see. Here is the probability of F, number of girls in a school. 430 upon 1000. Number of girls in a common part, 12th class and girls. That is 43 upon 1000. Now you want probability of E if F already happened. You can see here. E is the event student studying in a class 12th and F with a she is a student or girl. Yes, she is studying in a class 12th and it is a girl. Probability of intersection F upon probability of F. Put the values, you will get 0.1. This is the answer. Now example number 5. A die is thrown 3 times. Okay. First of all, you must know how to get the sample space when the die is thrown 3 times. As we know that when the die is thrown twice, we are getting 1, 1, 1, 2, and up to 1, 6. This is 2, 1, and up to 2, 6. 3, 1, 3, 6. And this is like this 6, 1, 2, 6, 6. Now 3 times means this 1, 1, 1 comes with 1, 1, 1, 3 times 1, 1, 1, 2, 1, 1, 3. It means 6 outcomes are there for one element. It means how many are there? These are 36 total and each are having 6. It means how many? 216 outcomes are there. How many outcomes? 216 total outcomes are there. Now, what is A and what is B now? A means 4 on the third throw. Now, you have to just do this in your mind. Get where you will get the 4 on the third throw. 1, 1, 4, 1, 2, 4. You have to just go for 2 and just imagine and write down on which element you will get the third element 4. These are the elements. 6 on the first and 5 on the second thrown is B. Get from the sample space. Intersection part is only one element. And you want probability means already happened is B. It means A if B already happened. Yes. Put the intersection value 1 upon 216 upon 6 upon 216 and you are getting 1 upon 6. Main part was that in this question, you have to know how many elements are there in the sample space and how many are in a A. That calculation matters in this question. Now do example number 6. Now here's a good example, example number 7. Consider the experiment of tossing a coin. If the coin shows head, toss it again, but if it shows tail, then throws a die. It means what? Experiment of tossing a coin is not completed after tossing a coin. After tossing a coin, you have to observe the coin. If you are getting the head, it means you have to toss it again. Again, you have to toss the coin. If you got the tail. In that case, you have to throw a die. It means experiment is completed. If coin shows head, then you will toss coin again. This is the first part. If coin shows tail and you throw the die, that's the second case of the experiment. After throwing the die, the experiment is completed in the second case. Now find the conditional probability of the event that the die shows a number greater than 4. Given is there is at least one tail. Given part is at least one tail there. Now head, then you have to toss the coin. Head, getting head with head. Head and tail. If you are getting tail, you are throwing a die. It means maybe with the T you are getting 1, 2, 3, 4, 5 and 6. Now this is the experiment where after one thrown you are not getting the same getting the result. After performing one activity, you are doing second activity to complete the experiment. So here is the different way to calculate the probability. Now yes, here is the tree given to you. Probability of getting head is 1 by 2. Probability of getting tail is 1 by 2. Now when head is there and you are again tossing the coin, you are getting again head. This is a probability of 1 by 2 into 1 by 2. This you are getting 1 by 4. Same here 1 by 4. Here tail is having probability 1 by 2 and 1 is having probability 1 by 6. So probability will be 1 by 12. In all cases it will be 1 by 12. Now how to solve the question? E and F, both events are here. F is having these elements, E is having these elements. Here is there is at least one tail is there. Collect the elements from the given tree. And in the E, the die shows number greater than 4. This is E. Now common part is this one. Now probability of, we want probability of F and intersection probability. Probability of F, as I told you, probability of HT is 1 by 4. T1 is 1 by 12. Add these, you are getting 3 by 4. Probability of intersection part, this is 1 by 12, this is 1 by 12, both are 1 by 12, is 1 by 6. Now probability of E if F already happened. If F already happened. Put the values 1 by 6 and 3 by 4, you are getting 2 by 9. This is the answer. This is a very good example and it's a different example. Now do exercise 13.1. Try the questions of 13.1. You can do all the questions. Questions are not difficult. After this exercise, we will discuss multiplication theorem on probability. As I have told you, probability of E if F already happened, you can calculate by using the formula probability of E intersection probability F and divided by probability of F. If I want multiplication theorem, what is the meaning of multiplication theorem here? Suppose I just rearrange this formula, that is E intersection F can be written as probability of F into probability of E if F already happened. Now here this is the intersection part and shows that multiplication theorem. This is the multiplication theorem. From the same formula we will get the idea of multiplication theorem. Let's see. Let E and F are two events associated with a sample space S. Clearly the set E intersection F denotes the event that both E and F have occurred. In other words, E intersection F denotes the simultaneous occurrence of the events E and F. The event E intersection F is also written as EF. Sometimes we write probability of E intersection F as probability of EF without any sign. This sign is but obvious. very often we need to find the probability of the event EF. For example, in the experiment of drawing two cards one after the other, we may be interested in finding the probability of event a king and queen. The probability of event EF is obtained by using the conditional probability as obtained below, as I told you above here. This is a multiplication theorem. Okay, same will be here in the next concept. Same is written here. As it is written here, probability of F if E happened. If it is probability of E if F happened is this one. If probability of F if E happened, then you can write like this. This is the formula. Same way to write down the multiplication theorem of the probability. Now here is the example number 8. An urn contains 10 black and 5 white balls. 2 balls are drawn from the urn, one after the other without replacement. What is the probability that both drawn balls are black? You are just picking the ball and you are not replacing that ball. Without replacing ball, you are picking the another ball. Now here you have to just give an idea of the probability that both balls are drawn are black. First ball, when you are picking from the bag, that is black, that will be, the probability is 10 upon 15. That is the 10 upon 50 when you are picking first ball. If you are not replacing that ball and you are picking the another ball, it means the probability of, it means black ball reduces. It will be now 9 and total is also reduces because you are not replacing the previous one ball. So it will be 9 upon 14. E already happened. That's why there is a change in the probability. So answer will be 10 by 15 into 9 by 14. This is the way to write down the probability of E. It means getting the black ball, first black ball, and getting the second black ball without replacing the first ball. We are getting 10 upon 15 into 9 upon 14. That is 3 upon 7. This is the solution of the example 8. Now, multiplication rule of probability for more than 2 events. If 3 events are there, then how to write down? This is the way to write down. Now, example number 9. 3 cards are drawn successively. 3 cards are drawn successively, okay, without replacing from a pack of 52 well shuffled cards. It means when you are picking the card, you are not putting back, you are just drawn second card and same as the third card. Now, what is the probability that the first 2 cards are kings and the third card, drawn card, is an ace? It means first 2 cards are king, you have condition, and third one is the ace. Now, out of 52 cards, when you are picking the card and it is a king, how many kings are there? 4 kings are there. It means probability of getting king is 4 upon 52. If you are not replacing the king and you are picking the another card, it means 4 upon 52, and next is what? 3 upon 51. Now into how many aces are there in the, how many aces are in the cards? There are 4 aces in the card. Here I am writing the same thing. 4 aces are in the card. It means there is a 4 and number of cards you are not replaced, 2 cards. So how many are left here? 50. It means 4 upon 52 into 3 upon 51 into 4 upon 50. That comes out 2 upon 5525. This is the answer. This is a way to understand the question of probability. Now, next concept is independent events. What are independent events? We have to check 2 events you have to given. You have to check whether the events are independent or not independent. Here's a formula to check the independence of the events. Let's Yes, here is the definition. If two events E and F are given to you and probability of event E intersection F is equal to probability of E into probability of F in case the events are known as independent events. If this formula verifies by putting the numerical values, it means the events are independent events. If these are not equal, it means events are not independent events. Okay. Now definition number third. E and F are the two same independent. I have told you definition number third. Now remarks are there. I think you have to read these remarks also. Here you will get an idea what is the difference between the mutually exclusive and the independent events. Actually, independent events, when we want to check, then at the time we want probability of the given events. But when we are checking the mutually exclusive events, and it means we are talking about the only events, not about the probability. It means mutually exclusive can be checked by taking the events only, and independent events can be checked by taking the probability of the events. So here you have to read two events E and F are said to be independent, dependent if they are not independent. It means if the formula is not equal, both left and right sides are not equal, it means events are dependent, not independent. Sometimes there is a confusion between the independent events and mutually exclusive events. Terms independent is defined in the terms of probability of the events. I have told you. Whereas mutually exclusive is defined in the terms of the events, subsets of the sample space. We are talking about the events only. It is events, it is probability of the events. Okay. Moreover, mutually exclusive events never have an outcome common, but independent events may have common outcomes. Clearly, independent and mutually exclusive do not have the same meaning. You must know about it. Which you have to, I think third point is discussed already. Now for the mutually independent events, if three events are there, then how to write down the formula? Let's do the example number 10. These are very easy examples. You have to check whether the events are independent or not. A die is thrown, is the event number appearing in is a multiple of 3, and F be the event, the number appearing is even. F, E, probability of E, probability of F, put the values. If left and rights are equal, then it means what? Events are independent. Put the values, numerically solve. Same example number 11. Check the independent events or dependent events concept. Example number 12. All these are very easy examples you can do. Let's discuss the example number 13. This is a little bit different than the previous examples. Prove that if E and F are independent events, it is given to you E and F are independent events. Then so are the events E and F naught. It means E and F naught both are independent events. It means we want to check, we want to show intersection of these should be equal to probability of E into probability of E F naught. You have to show this. Now here one Venn diagram is given to you. Venn diagram is showing that E is the event, F is the event, intersection part is this one, and E intersection F is this. And you can write the shaded part is E intersection F naught, and this is E naught intersection F. And the outer part is E complement intersection F complement. Now this is the way to give an idea of the concept. Where is E naught intersection F and where is E intersection F naught? Now it is given E and F are independent events. You can write probability of E intersection F can be written as probability of E into probability of F. Now probability of E can be written as E E. E is the union of E intersection F. You can see here E intersection F and E intersection F naught. You can write E as like this from the Venn diagram. You can see here, this is the whole E. You can combine these two by union sign. Now you can apply the distributive property. I think here will be E intersection. And now apply the formula of probability now, not distributive probability. Apply the simple probability formula. Probability of E is equal to probability of E intersection F plus probability of intersection F naught. Now probability of E intersection F as it is, and shift the statements from left to right. You will get here probability of E intersection F naught. This is as it is, and shift this to the left hand side, right like this. Now intersection F, it is given independent events hai. Probability of E into probability of F. Now take common probability of E, taking common, just a minute. Take common probability of E from these two, and here one is left here, 1 minus probability of F is, it means probability of F naught. So E and F dash are independent events. Now example number. Here is the highlighted part. Notice there, it can be shown that if the events E and F are independent, then E naught and F are independent, E naught and F naught are independent. Remember this concept. Now here's example number 14. If A and B are two independent events, it means now you have to show that at least one of A and B is given, that like this. At least of A or B means A union B. You must know the algebra of the sets. It gives you probability of A union B. It means at least one of A and B means probability of A union B. Apply the formula. Now probability of A intersection B will be equal to probability of into probability of B, because A and B are independent events. Now take the common probability of B. You will get probability of A naught. Now here you can replace probability of A by 1 minus probability of A naught. Now take common probability of A naught. You're getting 1 minus probability of B, and it is B probability of B naught. 1 minus probability of A naught into probability of B naught. Now I have just given the idea of the examples of exercise 13.2 and 13.1 to you. Now you have to try the questions of exercise 13.1 and 13.2. Do the questions. I will send you the PDF of the solution of 13.1 and 13.2. Do these two exercises, you are on. After that, only one concept will be there, that is a Bayes theorem. We'll discuss in the next video. Thank you. Have a nice day.